Welcome to Study Loop.
So now we'll work on problem 140 from chapter 17. Here we're told that we want a carbonic acid solution of a specific hydrogen concentration. So the question is, how much solid NaOH do we need to add? So the first thing that we want to do here is calculate the moles of carbonic acid in this solution. So since we have a 1 liter solution, the molarity is equal to the number of moles, so we have 0.1 moles of acid. Now, the pH that we're looking for is not initially apparent, but we're given hydrogen concentration that we want to shoot for, which is 3.2 times 10 to the minus 11. And if we take the negative log of this, we'll get the pH that we're looking for, which is equal to 10.49. So now we want to have a pH of 10.49 in a carbonic acid buffer. Since the pH, the pKa of carbonic acid, the first equivalence point, is much lower, is acidic, we need to assume that we're around the second equivalence point, which is basic, and would give us a possible value around 10.49. So we can write the Henderson-Hasselbalch equation as being pH is equal to 10.49 is equal to pKa2 for carbonic acid plus the log of base over acid. Now this is equal to the pKa2, which is 10.25, which is a close value here, so we know we're doing the right equivalence point, right Ka value. And then we have the log of CO3 2 minus, so this will be the second conjugate base. And then we have the HCO3 minus, which is the acid in this case. So if we subtract 10.25 from both sides and take the anti-log, we get this ratio of carbonate over bicarbonate is equal to 1.73. And we also know that whatever ratio of acid and conjugate acid we have, the total number of moles that are available is 0.1. So if we write moles of CO3 2 minus plus moles of bicarbonate, HCO3 minus, this must equal 0.1. So since we have two variables and two equations, we can go ahead and use them to solve. So we rearrange this equation here to say that the moles of CO3 2 minus is equal to 1. So first of all, we're going to rearrange this one. Let me erase this for clarity here. So we're going to use the first one to find the second one. So we're using this one. So moles of CO3 2 minus is equal to 1.73 HCO3. And so we can plug this term into this term, and we get 1.73 HCO3 minus plus HCO3 is equal to 0.1 moles. And so when we solve this term for the moles of HCO3, we get 0.0366 moles. It's important before the end of your calculations not to drop too many figures because the rounding may make an impact on the calculation. And so the next step is to go ahead and use this value of bicarbonate to calculate the amount of carbonate that we need. So the moles of CO3 2 minus is going to equal 0.1 minus this value that we just obtained, which is equal to 0.0634 moles. So now we get back to the question of how much NaOH do we need? So let's look at how much NaOH is needed. So first, we needed to make it to the first equivalence point. We needed to neutralize this amount of carbonic acid at the first equivalence point. So we needed 0.1 moles to reach first equivalence. Then, at the first equivalence point, all we had was HCO3 minus. So then we needed 0.0634 moles to convert the bicarbonate to carbonate. So if we add these two up here, we get that we need 0.1634 moles of NaOH, and we're asked for the mass. So if we multiply by 40.0 grams over 1 mole, this is 40, we get 6.54 grams of NaOH.